Okay, class, so this is a very, very important slide. So we're going to spend a good bit of time on this. What we're looking at here is the action potential plotted with time on the x-axis and the membrane potential on the y-axis. If you remember, we said that the resting membrane potential was negative 70 millivolts. So before we've done any experimentation, the cell is hanging out at negative 70 millivolts. At this point, we're going to apply the stimulus as it says here. Note the time scale. The entire action potential from beginning to end is 3 milliseconds, 3/1000ths of a second. So you can get 333.3 of them in there you go. The subtitles are doing great. So you can get that many 333.3 action potentials in 1 second. Now, when the cell is at rest at negative 70 millivolts, let's call this the polarized state. The way I think it is I imagine the globe. Okay, we have the equator, and we have the South Pole here, and the North Pole here. What I imagine is negative 70 is so far from the equator. If the equator is 0, we're hanging out way here at the South Pole, aren't we? So think of the resting state as polarized. All right, the polarized state. As you can see, depending on when you look, the voltage is going all over the place, right? At this point in time, okay, let's make it more clear. At 1 millisecond in time, we are roughly at positive 30, positive 40 millivolts. At 2 milliseconds, we're at something like negative 75 millivolts. At half a millisecond, we're at roughly negative 30 millivolts. Okay, so as you can see, we're going up and down. When the cell becomes less negative, so we're talking about moving this way. When it becomes less negative, we call that depolarization. You see, depolarized, if rest is polarized and you go towards 0, we call that depolarization. As you can see at this interesting area here, which we'll talk about later, the cell actually becomes more negative than rest. When the cell is more negative than rest, that's called hyperpolarization. Depolarization is AKA, also known as excitation. And hyperpolarization is AKA inhibition. Now, as you can see here, we have 4 different levels of stimulation that we're going to apply. If you recall this experimental setup, with our stimulating electrode, we can deliver any level of stimulation that we want. Here we're going to start with a very weak stimulus and get a little stronger, and a little stronger still. If you can, please just focus on number 1. Weak stimulus is given. Let's see what happens to our cell. Well, you will see that temporarily the cell becomes a little less negative. Temporarily, it gets up to maybe, I don't know, what does that look like to you? Maybe negative 66. But then quickly, the cell returns right down to rest. What this little blip is an EPSP. That stands for excitatory post synaptic potential. Now, some of you might be wondering, do we have a situation where the cell becomes temporarily hyperpolarized? We sure do. And those are called IPSP, where this is inhibitory. But for now, we're just talking about EPSPs, excitatory postsynaptic potentials. Now, look at stimulus level 2. We give a stronger zap, beep, and the cell depolarizes, this time a little bit more. What you see is the difference between stimulus level 1 and 2 is that the depolarization is a little bit stronger, and what goes up higher takes a little bit longer to come back down. So it's a little bit stronger EPSP, which lasts a little bit longer. However, that's it. It peters right out and nothing much comes of it. Same with stimulus level 3. A little bit stronger stimulus, lasts a little bit longer. So 1, 2, and 3 are all ignored. Remember we talked about the basic job of a neuron, and a big component to that was this threshold, this level of excitation that the cell must reach before an action potential will be generated. Finally, we're going to give stimulus level 4, and something very different happens. With stimulus level 4, we depolarize, 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 and then boom, we hit this very key orange line. Okay, sorry about that. I'm still getting used to this. This threshold of X. Okay, this threshold of excitation has been reached. Now, once you hit this critical level, let's call that negative 60 millivolts, you will, and I mean will, always generate the entire action potential. It is inevitable. As soon as you reach the threshold, you will generate an action potential. The action potential is known as an all or none phenomenon. So you either get the whole shebang or you get none of it. As you can see, you either get these little nothings or you get the whole big thing. By the way, there's another term for threshold of excitation that I like even better, and it's the critical firing level, CFL. Now, a couple of notes. The resting membrane potential does not change. It is definitional. And I can also tell you that the critical firing level or the threshold also does not change. Okay. Now let's look at the action potential. You'll see that it rises to roughly positive 40. And why don't we call it positive 40? So so far we've talked about three critical levels: negative 70 millivolts, negative 60 millivolts, uh, uh, and now positive 40 millivolts. You see the action potential quickly comes right back down towards baseline, but it has this overshoot. So for a period, we are actually hyperpolarized. Later, of course, I'll explain to you exactly what's going on here. But for now, keep that in mind and note that it gets down to about negative 70, let's call it negative 75 just to keep it simple. By the way, always be mindful of your units. Units are obviously everything. Okay, now I want to take us back to the hot iron versus the hot stew and talk about what happened and the differences between the two. Now, if we do some simple math, it takes a 10 millivolt stimulus to get us from rest to threshold. So let's imagine the iron. Let's see if I can draw an iron. Old school iron. There you go. Boy, that's terrible. Wow. All right, whatever. The iron, let's say it gave 15 millivolts of stimulus. Then you could understand easily why a 15 millivolt stimulus would cause us to withdraw our arm, because it would take us beyond threshold. But remember I said the stew. Oh man, I'm gonna get better at this. I think there's only one way to go, I suppose. Ooh, it's hot. All right, so the stew is also 15 millivolts. Why don't we drop the stew? Remember when we were working with the stew, we valued the stew. We were surprised by the iron. We were not surprised by the stew. We were carefully going to take the stew to our dining room table with our candle for our date. But if it's 15 millivolts, why don't we drop it? Because we were under inhibition. The big inhibition. When you're inhibited, you are not at rest, because rest means rest. Rest means neither excited nor inhibited. While we were getting ready to take the stew from the stove to the table, we were under inhibition. That means we were no longer hanging out at negative 70 millivolts. We may have been down at negative 80 millivolts. Now, you could do the simple math. From negative 80 millivolts, a 15 millivolt stimulus is not going to get us to threshold. So you don't drop the stew, and your date works out, and everything is good. But your body's not stupid. If the stew were so hot that it's going to melt your fingers and cause tissue damage, then it wouldn't be 15. Let's say it was 25 millivolts of stimulus, super hot stew. Then even if you're hanging out at negative 75 or whatever, no, sorry, we said, even if you're inhibited hanging out at negative 80, a 25 millivolt stimulus would make you drop it. So your body's not dumb. It will have to protect itself at the cost of your stew, even though you've been working so hard. All right, I hope that all made sense and my drawings weren't too silly, but I can't help it.